Okay, thank you very much. All right, Assalamu alaikum and good morning to all of you. So, first of all, thank you very much to the MACE panel for giving me the opportunity to talk on this Monday MACE talks. All right, so for today, my topic is IoT based dynamic scheduling for task computation. Okay, so now as we all are aware that IoT has taken a substantial lifestyle for us. So, and in the coming days, I mean, it won't be wrong to say that IoT will be a necessity for all of us than requirement. So yeah, so first of all, just a quick glimpse that what exactly an IoT is, right? And some quick facts about the IoT. So yeah, basically the IoT is an emerging technology where the machines are embedded with sensors that allow them to relate the data to each other. So in a broader perspective, so that could be taken as the definition of the IoT. Now, the big businesses are already investing billions into this concept. Like in 2008, there were more devices connected to the internet rather than the humans, and by this 2020, these numbers are going to go up to 50 billion, right? And it will make business more efficient, and as a GDP it would add up to 15 trillion dollars as an additional amount. So this is a huge number. And uh, and this signifies that what IoT is going to do to the economy in the future. So this could be yeah, taken as the serious parameter to be dealt with, right? So if we take in terms of the healthcare system, so in that regard, the IoT could save lives, as it has an enormous role to play in the healthcare, whereby let's say if any patient gets an heart attack or something like that. So also in that context, the relevant data of the patient's history could be transmitted to the doctor before the patient arrives to the hospital. So that is pretty much a faster service, right? So what is wrong to leverage on the IoT if it is able to save lives in terms of, if you talk in terms of healthcare? Okay. And now the fourth fact is that in with regard to the Wi-Fi development. Okay. So with respect to the Wi-Fi development, it will make the IoT working more better, whereby if the Wi-Fi signals itself are converted to the DC current, right? So DC current and the low power sensors devices, if we are connect if they could be connected to the same energy level loop, then that could work in tandem, right? That could work in tandem, and it could provide a smooth workflow whereby all the devices could be connected within the same energy loop, right? So the last fact about the IoT is with respect to the security issue, right? So when we have like uh, n number of devices connected to the internet, so obviously there will be an issue of security. And yeah, with coming days, that is one of the most important factor to be dealt with, because the services comes handy in the security. So we have to deal that parameter in a very stringent manner, right? Because the security parameter cannot be neglected, and that is one issue which needs a lot of attention, to resolve. Okay, so now, like I have said, that IoT is not just a technology. I mean, it would be rather taken as a necessity, right? Because that will become a necessity in the upcoming days. So okay, we have a different number of strands with respect to IoT. That could be smart planets, smart cities, smart buildings, smart transport, smart energy, smart industry, smart health, smart living. So, all these things is nothing but an ecosystem with respect to the IoT. And this is nothing but our lifestyle in the future, right? So this everything will be connected to each other, and this could be taken as a whole ecosystem, okay, whereby every strand is interconnected to each other, and every strand is important, equally as important with others. So this is nothing, this will be a kind of a necessity in future. So we as a humans, we have to adapt with this kind of
Not just the
ecosystem technology. I mean, it would be rather okay. So what exactly the problem is? Okay, we have IoT solutions right now. What exactly is the problem with the interconnection of such devices to the internet? Okay, so what is the problem basically? So we'll just try to highlight and focus on those problems. So the rapid evolution of the IoT market has caused an explosion in the number of variety of IoT solutions, right? Then additionally, large amount of fundings are being deployed at the IoT startups to manage these IoT solutions. Okay, so in that regard, the startups are already helping the firms so that this would be synchronized and managed, the IoT solutions. So consequently, the focus of the industry has been on manufacturing and producing the right type of hardwares to enable those solutions. Okay, you see now, with respect to the IoT solutions, the industry is still like on the hardware level. Okay, so like in other terms, we can say that okay, we are just like more interested to give you the solution, but how to manage multiple solutions, that we still don't know. So that is one thing to be worked upon. Like in the current model, most IT solution providers have been building all components of the stack, from the hardware devices to the relevant cloud services, or as they would like to name it, as IoT solutions. So as a result, there's a lack of consistency and standards across the cloud services used by different IoT solutions. Okay. Now, when these devices are being connected to the cloud, so what happens is that okay, it is stored in the cloud. I can say that it's not in a very structured manner. Okay, I mean, it's just placed over the cloud. I mean, now the mechanism which has to take place over the cloud, now that is not clear as of now. Okay, that means how the data has to be scheduled inside the cloud. Okay, and when the data comes from, let's say, from any let's say the center of the cloud, it comes to the edge of the cloud, right? So there's no such defined way that how this data should be scheduled inside the cloud. Of course, as an IoT device, all the devices has got its own instance over the cloud, right? Even as a user's profile, the user has got its own instance. But what is the scheduling mechanism inside the cloud? So basically, uh, as of now, the focus of the industry is not at that paradigm. So rather than that, the focus is at the device level right now, as of now. That what is the compatible devices, to comport with the different kind of algorithms. Okay. So now, as the industry evolves, the need for a standard model to perform common IoT backend tasks such as processing, storage, and firmware updates is becoming more relevant. So, so what I mean to say is that there should be a standardized backend, a standardized backend to schedule the task based on the structured data. Okay, now we all know that at the cloud the data are in the unstructured format. Okay, now there should be some criteria to structurize those data first, right? So okay, so coming up with such kind of model or paradigm, which is like could be considered as a standard. Okay, so that will be a very challenging task. Okay, because that is nothing but the next layer. Okay, after the device level, that is the next layer which has to be dealt with, because like I've said, the IoT, once the IoT becomes a necessity, and if this kind of like the scheduling standard mechanism are not defined, then it, of course, it will be it will be a challenging phase for the users, right? So to get compatible with such technology, so some standardization of the mechanism at the cloud, it is more actually important. All right, so yeah, so let us we can just try to focus something on the scheduling paradigm over the cloud. Now, all right. So basically, with regard to the resource management at the cloud, can be distributed or can be categorized into four strands. That is the resource type, objective, the resource location, and the resource use. Right. So actually, it's a very there are very vast parameters involved in these four strands. So for the current talk, we can just try to focus on the objective strand. So whereby we have resource allocation, placement, migration, and scheduling. So for today's talk, will be more focused towards the scheduling mechanism, okay, which will take at the back end. So yeah, but nonetheless, all these four strands are very important and has to be dealt in tandem, whereby each strand should comport with each other, right, to make the workflow more smooth. So as of now, we can just try to focus on the scheduling mechanism, which could take place at the back end of the cloud. So, all right. So this is one pictorial overview that how the how the devices communicate with the cloud, and how is the offloading at the both ends takes place. Okay. Now, if we see in this picture, in this image, so uh, we can say we can see a edge of the cloud, we can see, right? We can see an edge of the cloud. So basically what happens is that whenever the data wants to offload to certain device, right? So either it could be transmitted from the center of the cloud, or it could be transmitted from the edge of the cloud, right? So, okay, now when the data is wants to transmit from the center to the edge, so it has got some own scheduling mechanism which has to be clearly standardized. So, but rather than that, the data could also be transmitted from the center of the cloud. Okay, so in that regard, so each device has got its own task time share. So as per that task time share, the offloading takes place either into the cloud or onto the device. So that is basically on the defined on the defined task time share. Okay, and in between the task time share, with regard to the multiple devices, there could be a latency. Okay, now how that latency will affect the overall offloading onto the device or onto the cloud, so that we can discuss. But as per the defined task share, some kind of priority could be assigned at the algorithm level inside the cloud, right? Some kind of priority that could be defined, and with respect to that priority, the offloading could take place either in a preemptive manner or in a non-preemptive manner. Okay. Now, in this regard, it is very important to know that what all tasks could be preempted or interrupted. Let's say that if the task is highly very important, a hard real time task, now it will not be appropriate to stop that task or to preempt that task even for a while, okay, because that's a hard real-time task. So one cannot a lower priority task or a middle priority task cannot preempt that task in between, even for a short while, because that's a hard real-time task. So in this regard, it is very important to structure what are the critical tasks or the hard real-time tasks, and what are the non-hard real-time tasks or non-critical tasks. So it is very important to structure those kind of tasks over the cloud. Okay, so there should be some kind of mechanism which could structure those kind of tasks, and it could abstract that into certain functional modules. So let's say that if the critical task and the non-critical task, or the middle priority task or the mid critical task, if that could be, if these kind of tasks could be abstracted into a functional module over to the cloud, so that could be one of the promising way to schedule the task. So if we are able to structure, the task as per, like I've said, in the category of the critical, non-critical, and the mid-critical. So okay, so let us check in terms of the order of offloading. So in a typical manner, so this will be the order of offloading onto the device. So yeah, that could be taken in terms of the first come first serve. So that is what being happened here. So this one is the T1, T2, T3, T4, and T5. Okay. So in this way, the offloading is taken place in the first come first serve basis. Right. Now, if we want to, if let us say that we want to offload in terms of the shortest job first. So in this regard, we can see that, okay, this is the L2 is the shortest job. So we can revamp the order in terms of offloading for the shortest job first. So that will be what? That will be task number 2, task number, okay, we can say it's k, then it's k minus 1, then it's 1, then it's 3. So this is also, like, this is just a typical example of loading with respect to the size of the task, right, in terms of the time. So yeah, this is one way. There's one way to offload the task, right? Now, but before offloading the task, it is also very important to determine the task processing ability at the device level. So in that way, also the task could be mapped from the cloud or to that certain device, which has got its own capability to process. So this is also one way to distribute the task to the device from the cloud. So okay, with this, we have just had an overview of how these tasks could be mapped from the cloud to the device. Okay, so this is one way. But like I've said, that how can we structure the data over the cloud in terms of its priority? Okay, so let's say that if we get some kind of mechanism, if get some kind of mechanism whereby we can do the abstraction into a functional modules of all those critical and the non-critical tasks, then that would be a promising manner to schedule things up. So let us say that in that regard, if we design a functional module, okay, okay, let's say these are one functional module, right? So in this case, this could be considered as the functional module for all the hard real-time tasks. Okay, so let us say that if in this case, if the first request is issued at cycle number 12, okay, and if let us say that if it is a 4-beat burst request, then if it's a 4-beat burst, then its acceptance is given at the cycle number 16. Okay, and at cycle number 16, the request is granted and the execution starts till cycle number 30. So I mean, so this is the defined task cycles for this first request. So over here we can see is that the defined task cycles for this request is 24. So it is going from 16 till 30. Okay. Now at cycle 30, again a second request is issued. Okay. So the second request issued, then again the second request is a 4 beat burst request. So from 30 to 34. So at 34, at cycle number 34, the second request is getting the permission to get executed, and then the second request starts its execution, and it starts its execution till cycle number 44. So over here we can say is that the execution time cycle of the second request is nothing but 10, right? So it's going from 34 to 44. Okay, and then at cycle number 44 the execution time ends. So the main thing is that this kind of master cannot be blocked. Now over here I cannot see any request coming in between cycle number 16 or cycle number 30. Similarly, I cannot see any third request coming between cycle number 34 and cycle number 44. That means I'm allowing each request to complete its cycle first. I mean, no request can interrupt in between. That means these kind of tasks cannot be preempted. Okay, so this is taken as a one functional module. Okay, whereby we can place all the high priority tasks. Okay, so this could be abstracted into this functional module. Now, if we look towards the second functional module, then let us say that we have named this as paired parallel underscore type master. Okay. Now this is also same as the preeminent master. Okay. But the only difference is that over here we have defined a strict guideline to finish the task execution time. Okay, that means we have defined a limited number of cycle within which the task has to be completed. Okay, in this case, okay, we have got two requests. So one is represented by the bidirectional line, and one is represented with the unidirectional line. So over here, you can see we can see is that the requests are allowed to be issued during the execution time of the previous cycle. Okay, so in this case, the request can be issued, right? But it cannot be granted the permission to execute until the previous cycle finishes. Okay, that means that okay, if the request is allowed to be issued, that means the scheduler uh, can uh, uh, can overcome the latency time. Like, I mean to say that the latency in this case will be reduced, because the scheduler already knows that okay, there is some request which has been issued or which is continuously being issued. So immediately when the previous cycle of finishes, so the new cycle from the other request could be started immediately. So there will not be a latency in between the start of the new cycle and the previous cycle. So there will not be a latency, because there was a permission there was a permission given to issue the request in between the previous cycle. Okay, now when the request is issued, that time pauses for a few seconds. Like, okay, it's up to the design constraint of the scheduler, but there is preemption. Okay, so let's say if the task is not that critical, or a very critical task, so it could be placed into in such kind of functional module. Okay, so that the latency could be avoided. All right, so this is with respect to the paired parallel type master. Now, if we look at the third master, so that is the dependent paired parallel type, or the DPP type master. Okay, in such kind of master, it is like different from the previous two. Okay, but the matching criteria is that it has also got a real time cycle limitation. That means it has got a defined execution time, right? And in this also, the request could be issued in between the execution of the previous cycle. So in this, the requests are allowed to be issued, and moreover, the request of the new cycle could be granted even if the previous cycle has not finished. That means there is some kind of synchronization along with the parallel implementation at the last phase. So this is one way where the parallel implementation could be taken into picture. That at the last phase, the implementation is done in the parallel. Okay, let's say that if in this case the first request is issued at cycle 7. Now if I say that the first request is a 3-bit burst request. Okay, if it's a 3-bit burst, then its permission is granted at cycle number 10, and then from cycle number 10 till cycle number 14, the first request gets implemented. Okay, now if there's a fresh beat burst involved here, that means it's a fresh request. So, and this request was not being continuously issued at the previous cycle. So there's a new request with 3-beat burst, and it gets executed at cycle 10, and it finishes at cycle 14. Now, during the execution of this first request, a new request is issued. Okay, that means second request is issued, which actually was being issued before the first request permission was granted in cycle 10. So the second request basically got issued at cycle 8. Okay, so now we can see here is that the second request is issued at cycle 8, but its permission is granted at cycle number 13. Okay, so now we can see a kind of a overlap here, because we can see here is that the cycle from the first request has not yet completed, but the cycle of the second request has started at cycle number 13. So there is some kind of overlapping here, you can see. Now this overlapping, we can just take it in terms of the synchronization and the parallel implementation to save the time. Okay, so we can see is that with such kind of scheduling paradigm, and if we try to structurize the data into such kind of functional modules, then all the hard real-time tasks could be finely synchronized. Okay, so this is one way to synchronize the mechanism over the cloud, because this is one thing which has not been taken into account as of now. Okay, so basically this all comes under a clear cut arbitration strategy. So in that respect, so this is a small pseudocode of the arbiter. So like we have discussed, the first priority is always given to the hard real-time task, which is taken care by the preeminent type of master. The second priority will be given to the paired parallel type master, that is the second master which we discussed, and the third priority could be allotted to the dependent pair parallel type master, the DPP type, which is the third type which we have discussed, where the parallel implementation was to be seen at the last phase of the cycle. So yeah, this is how is the if else condition for the implementation of all these three masters. Now, yeah, it is very important to note that we need such kind of arbitration strategy inside the cloud level. Okay, so using this arbitration strategy, these the different kind of master modules could be managed, and how the data could be structured into these master modules. Now this is another topic, that how in what regard we can structurize the data into these three functional modules. So for that we can take many factors into consideration, that maybe we can take cost optimization into consideration. We can, in that regard, we can use, let's say, greedy level algorithm into consideration, and then accordingly, the data could be structurized into these kind of functional modules, into these three kind of functional modules. So this is like just one way to how to structurize the data into these functional modules. Okay, now packaging and deployment over the cloud. Okay, so maybe this is the absolute notion which has to be taken into consideration if we want to schedule things up over the cloud. So in that regard, we can just give some conclusive remarks now. So the key lies in packaging the proper scheduling mechanism over the cloud, and the trading of latency with task synchronization is essential. Okay, so the latency, we need to overcome the latency by doing task synchronization and parallel implementation. Okay, so this is like one way where this latency of generating the beat burst could be avoided. So with advances in cognitive technologies, the ability to process varied forms of information, vision, and voice have also become usable and open the doors for in-depth understanding of the non-stop streams of real-time data. So, like I've said, that to structurize these data, to structurize this kind of data, we need a proper mechanism. Okay, so either we can switch to some kind of like greedy algorithm to whereby the data could be allotted to these functional modules. Now, the factors driving adoption of intelligent action within the IoT uh, can improve the machine functionality. Okay, I mean, with these kind of adaptive algorithms, the functionality of the IoT could be improvised up to a substantial margin over the cloud. Okay? And this will smoothen up the workflow. Okay, and the other thing which could be taken to structurize the data could be done by the deep learning. So the deep learning could be applied over the cloud, and using that, the data could be structurized into these functional modules. So in that regard, also a proper and smooth scheduling mechanism could take place over the cloud. Okay, so the way ahead now, the way ahead could be, yeah, the IoT is an ecosystem of ever increasing complexity. So it is the next wave of innovation that will humanize every object in our life. So it is the next level to automate every object in our life, and convergence of technology will make IoT implementation much easier and faster, which in turn will improve many aspects of our life at home and at work and in between. So, like I've said, that in future this is gonna be a necessity. So, if we want to smoothen the workflow, then we need to apply some kind of standardization at the back end of the cloud. So this will basically improvise the whole network actually. So yeah, so one possible outcome of successful standardization of IoT is the implementation of IoT as a service. Now let's say that if we take this IoT as a service based, if with respect to IoT, if the service sectors could come into picture, then this kind of mechanism could be initiated in a very early in a very early time period. Okay, because as of now, the industry is working at the device level, whereby they are looking for the possibility to comport it with different kind of algorithms. But if we take the IoT as a service, then this kind of mechanism which has to be taken place over the cloud could be looked upon at a very very early stage. Okay, so we don't have to like wait for like higher period of time, whereby the scheduling mechanism over the cloud is coming at a later time. Rather than that, if IoT is taken as a service, then it could be worked upon from now on. So that is one way. One possible outcome to overcome this scheduling problem. Okay, so just on a positive note, here's the optimization outlook for the IoT, whereby the 12% enhanced consumer experience are to be seen. 16% changing the way we work and live in. And of course, in terms of pollution also, we can see that there's a 10%, yeah, reduced pollution. So these are nothing but a overall figure for the optimization for IoT as a positive note. So, but we have a lot to we have a lot to deliver in terms of IoT, and I hope it goes well with the coming future. So that's all for my talk for today. And if you have any questions, you can please post. And yeah, that's all there for. So thank you very much. Yeah, so thank you very much. So this was all about my talk today. So now I pass over to the to Miss Nani.